Okay, this is lecture number 14, in which we are going to begin with three-dimensional geometry. Basically, in space there are three coordinate axes, x-axis, y-axis and z-axis, which are mutually perpendicular. So vector along x-axis, unit vector along x-axis is I, unit vector along y is z, and unit vector along z is k. So if we consider IJK based system in three-dimensional geometry, then every point in space will have some coordinates, and those coordinates will be order triple x comma y comma z. So in this diagram I have shown that there is x-axis, y-axis and z-axis, all of them are perpendicular to each other. This is our origin, and let any point A in three-dimensional space whose coordinates are L, M and N, and to start with, let us consider the length of OA equal to 1. So vector OA is going to be Li plus Mz plus Nk. We will try to do all the calculations in vectors and then check what is its version in three-dimensional geometry. We need to be really good in both. I mean, sometimes you are required to solve problem using 3D geometry, 3D coordinate geometry, and sometimes you are required to solve the problem using vectors, equations of vectors, using equations using vectors. Okay, so from here to there you should be going from this place to that place, vectors to 3D and 3D to vectors, you should be comfortable and you should be really skillful in doing that. So if OA is unit vector, it can be written as Li plus Mz plus Nk. And now we are interested in finding out what do we mean really by this L, M and N. So we take OA dot I. If we take dot product of OA with I, it is going to be only L, because I dot j and I dot k, they are going to be 0, they are perpendicular to each other. Therefore L is going to be cos alpha. M, if we take dot product of OA with j, we will get M as cos beta, and if we take dot product with k, we will get N cos gamma. Now these coordinates element of any point in three-dimensional space, if OA is a unit vector, then they are directly the cosines of the angle. What is that angle? OA is making with positive x-axis is alpha, OA is making with positive y-axis is beta, and OA is making with positive z-axis is gamma. So cos alpha, cos beta and cos gamma are the coordinates of a unit vector in three-dimensional system. They are called direction cosines of that particular vector. OA's direction cosines are L, M and N, which are cos alpha, cos beta and cos gamma. And alpha, beta and gamma are known as direction angles, direction cosines and direction angles. However, every time your vector OA is not going to be a unit vector, so A can be any point in three-dimensional space. Let us call that point B. So OB is a vector which looks like, say, L1I plus M1Z plus M1K, and it is any vector and having not exactly unit length. So what will be the length of OB? It is simple. Length of OB, you may calculate the length of OB, find out what is the length of OB, that is yet another exercise. However, here one thing which is important to know is L square plus M square plus N square. That means if we take OA dot OA, OA dot OA, so if we are taking dot product with Li plus Mz plus Nk, we will end up getting L square plus M square plus N square is going to be equal to cos square alpha plus cos square beta plus cos square gamma, and that is what is going to be the length of vector OA, which is 1. So if element are direction cosines, then L square plus M square plus N square is equal to 1, and that is cos square alpha plus cos square beta plus cos square gamma is equal to 1. So this is the identity that we have with us. What does this identity mean? It means you do not have flexibility for all the three angles. This identity is always going to be true in three-dimensional coordinate system, because if you have, suppose if you change alpha, if you change beta, then you do not have a choice of changing gamma. All the three cannot be simultaneously changed, and therefore this identity is important. You have degree of freedom 2, so you can actually change two angles and automatically the third angle will be fixed, because cos square alpha plus cos square gamma plus cos square beta is going to be equal to 1. So OB is any other vector, and now these L1, M1 and N1 are the coordinates of point B. B, what is B? B is L1, M1 and N1. So if we really want to convert this OB into a unit vector, then we should divide them by radical L square plus M square plus N square, because the length of OB right now is root of L square plus M square plus N square, and therefore L1 upon radical L square plus M square plus N square, M1 upon radical L square plus M square plus N square, and N1 upon radical L square plus M square plus N square. That is going to be actually something similar to L comma M comma N. So I will write it for one. L, which is a direction cosine of vector OB, is equal to L1 divided by radical L1 square plus L1 square plus M1 square plus N1 square. What will be M? Similar, M1 upon the same quantity, and N also will be equal to N1 upon same radical quantity. So these are going to be the corresponding element for OB unit vector. If OB is considered unit vector and you don't consider the longer vector, just consider the unit vector, then the coordinates of the end point of that unit vector will be L1 upon this. Okay, this is understood. So in that case, these L1, M1 and N1 are not directly direction cosines. They are not directly direction cosines, but these numbers are proportional to direction cosines. So therefore these numbers, any numbers which are proportional to direction cosines, are called direction ratios. Okay, so direction ratios will tell you in what direction from origin that point is with respect to x-axis, y-axis and z-axis. That is the meaning of this word direction ratio, and that is what is actually fixing the direction of a vector in three-dimensional space. So this is the basic work which we are required to understand as far as three-dimensional geometry and its connection with the vectors is concerned. Okay, so if we want to really now find out the angle, the next activity is, suppose I give you A, which is L1, M1, N1, and B, which is L2, M2 and N2, and we are supposed to find out the angle between OA and OB, the angle between the two vectors OA and OB. Then what do we mean by that? Now let us consider OA and OB to be unit vectors. So these are direction cosines directly now. L1, L2, L3, L1, M1, N1, L2, M2, N2 are the direction cosines. So what will be the angle between them? The cos of angle theta is equal to, we know, A dot B upon absolute value of A into absolute value of B. Absolute value of B. But as I said, OA and OB are unit vectors. The denominator is going to be 1 and 1. So we need to take the dot product of OA and OB. You will observe that L1I dot L2I is going to be L1 L2 plus M1 M2 plus N1 N2 is going to be upon 1, is going to be your cos of angle between OA and OB. So this is one thing that we need to know. And suppose L1 L2 plus M1 M2 and plus N1 N2 is equal to 0. That means the cos of the angle is 0. That means the OA is perpendicular to OB. So the condition, this is numerator is equal to 0, theta is equal to pi by 2. Okay. Now here we give one example which is written there. Suppose A is 1, 2, minus 1, B is 2, 0, 3 and 3, C is 3, minus 2, 2. Find the angle between AB and AC. So AB, vector AB is going to be equal to B minus A. So 2 minus 1 times I, 0 minus 2 is 2 times J, 3 minus 1 is 4 times K. This is vector AB. And now this 1, 2 and 1 minus 2 and 4 are L1, M1 and N1. They are direction ratios of vector AB. Now vector AC is 3 minus 1 is 2I, minus 1 minus 2 is minus 3J, and 2 minus 1 is plus 3K. So these are the two vectors that we have now, and we are supposed to find out the angle between AB and AC, and we already have the formula L1. So cos of angle theta is equal to 2 into 1 is 2, minus 3 minus 2 is plus 6, 4 into 3 is plus 12, so it is 20 upon. Now here they are not unit vectors, therefore mod A and mod B, these values will be present there. So radical of 1 square plus 2 square, that is 5 plus 16, that is 20, and radical 4 plus 9, that is 13, plus 9 is 22. So the answer is 20 upon radical 20 into radical 22. Whatever simplification happens is going to be the final answer, and this is what is the cosine of the angle between these two. So practically you can think in terms of vectors and solve three-dimensional geometry problems, because we have learnt vectors first followed by 3D geometry. Okay, so after giving you this brief introduction about 3D and how to deal with direction cosines, direction ratios, let us directly try to find out what is the equation of a plane in three-dimensional geometry. So in vectors, equation of plane was P r dot n cap, unit vector n, which is perpendicular to the required plane, and if the distance from origin is P. So now we were supposed to convert this into three-dimensional geometry, and therefore the procedure for all subsequent calculations are also going to be the same. So therefore I am demonstrating you right now how do we get into 3D geometry using what we have already developed in vectors. So R will be equal to xi plus yj plus zk. So this is the xyz, x comma y comma z is any general point in three-dimensional space. Now unit vector, suppose it is a unit vector n cap, which is equal to ai plus bj plus ck. Of course, what I mean by this is a square plus b square plus c square is 1. That is what is inherent in this, because this is a unit vector perpendicular, and p is your distance. So now if I take r dot n, what is going to happen is a into x, that is, so r dot n LHS is equal to ax plus by plus cz, that is what is LHS, is equal to p, which is a distance from origin. So this is what is a Cartesian equation of a plane, which is degree 1 equation in 3 variables x comma y comma z. Now here, if we wanted to guess this equation without doing any calculations, it would have been the same, because what is the equation of point in one dimensional system? Ax is equal to b is the equation of point in one dimensional system. What is the equation of line in two dimensional system? Ax plus by is equal to c of line in a two dimensional system. And therefore, if we extend this, if mathematics is great, if God is great, then what would be the equation of plane in three dimensional system? We would have guessed ax plus by plus cz is equal to d of plane in 3D, and it is exactly the same over here. Because we have taken n as a unit vector, we have got this equation in terms of p. Otherwise, if that r is equal to r dot n, any general perpendicular vector is equal to q, and q is not the distance from origin, it is a real number. If we take it in this form, then r is same, n is again, suppose we take a dash n bar is equal to a dash I plus b dash j plus c dash k, then our equation would have been a dash x plus b dash y plus c dash z is equal to q. Instead of q, I can always write d here, d maybe d dash, and it would look like equation like this. And now if I want to really find out, so in this equation, in general equation, what do I mean by a dash, b dash and c dash? The coefficients of x comma y comma z, those are going to be important numbers for us. A dash, b dash, c dash over here are the direction ratios of the vector which is perpendicular to the plane. If this equation is of a plane, then what are the direction ratios of the vector which is perpendicular? Suppose I give you 3x plus 4y minus 2z is equal to 7. Suppose this is the equation of a plane, then what is the vector which is perpendicular to this plane? It is 3i plus 4j minus 2k. It is 3i plus 4j minus 2k. That is the perpendicular vector, because if this is the equation of plane, then the n is going to be along 3i plus 4j minus 2k. So that is what is important, and we get those coefficients back over there. And now if we want to really find out, this is general. Now if we want to find out the distance of this plane from origin, we might as well divide everything by radical a dash square plus b dash square plus c dash square to make every coefficient equal to cosine of that angle, direction cosine. So we have to divide RHS also by a dash square plus b dash square plus c dash square, for not changing the value of RHS. Therefore, this is what d dash upon radical a dash square plus b dash square plus c dash square is the distance of this plane from origin. In this case, what will be the distance from origin? 7 upon radical 9 plus 16 plus 4 is going to be the distance. Now, this is again analogous to what we have done earlier in two-dimensional geometry. We have seen x cos theta plus y sin theta is equal to p. That is what was our equation of a straight line in normal form. And what is this cos theta, sin theta? They are playing the role over here of direction cosines. So cos square theta plus sin square theta is 1, and therefore in the RHS directly you get the distance. So suppose I was given that 3x plus 4y is equal to 5 is the equation of straight line. I make sure that this 3 I should divide the whole equation by 5, which is 3 square plus 4 square, and hence 3 by 5 I will consider as cos theta, 4 by 5 I will consider as sin theta. Therefore the RHS that you end up getting is the distance of that straight line from origin, which is 1. This and this is exactly same. This is happening in 2-dimensional geometry. This is happening in 3-dimensional geometry. So we have found out the equation of a plane in 3-dimensional system using coordinates. It is very simple equation: ax plus by plus cz is equal to d, or you can refer it to ax plus by plus cz plus d is equal to 0, or minus d is equal to 0. So this is the beginning of 2-dimensional geometry. In the next lecture we will find out equations of planes, equations of line, then distance of a point from plane, distance of a point from line, then distance between two parallel lines. These are the things that we should do in the next lecture, and that should make you solve as many problems. If you have gone through these 13-14 lectures, then you should be able to comfortably solve majority of Sen gauge problems, which you should try. You have plenty of time now. You should finish all the problems, and there could be few problems which are based on tetrahedron or which are based on sphere, which we will deal with in subsequent lectures. Otherwise you will not have any problem in solving the Sen gauge exercises or any other material that you are referring to as far as vectors and 3-dimensional geometry is concerned. It is very important that while studying you go through these lectures and you try to visualize the things as much as you can, and try to get all these results independently yourself, so that if you spend good amount of time on theory and imagination, solving problems is not going to be difficult. Okay, thank you.